Please let me know if I'm too loud or too low. Thank you for coming. The title of this presentation is Form Follows Information. So I decided to find a common theme to run this through so it's easy on everybody to follow. So I've used form as a kind of concept that would link the different arguments that we're going to go through today. So as I was invited to join this conference, I began asking myself, first of all, what is technology? And second of all, what is collaboration? Technology because it's the theme of the conference, and collaboration because it's something I'm personally interested in within my teaching and research. So in this presentation, I will try to demonstrate the benefits that we can gain from technology, but not necessarily within our own domain, but also outside from our distinct body of expertise through reaching out to other disciplines. And I will try to show the value of using particular types of technology within the right circumstances and within the right context. So I guess one part of the argument would be that technology is not necessarily important per se, but it's only as important as the context in which it operates, as we've seen throughout history and throughout contemporary practice. The contents of my lecture, as I said, are tying into form. So we will talk about how form has been known to follow function, forces, mathematics, data, culture. Finally, focusing a little bit on software, hardware, and my concluding remarks would talk about expertise. So one of the first people who spoke, one of the first scientists who preached the value of technological collaboration or collaboration among scientific disciplines was Norbert Wiener, a mathematician in the late 1950s who wrote a famous treatise called Cybernetics, Control and Communication in the Animal and the Machine. So if you bear with me, I would like a little latitude within our understanding of the word technology. If you can try and perceive technology not necessarily as a system of mechanical parts, but rather as any kind of driving force behind a project, in which case the technology for Wiener's support of collaborating among disciplines was the in-between, what he called the gray field between the sciences that he found promising. And in this case, one of his projects was the collaboration he did with one of the medical doctors at the Harvard Medical School, where they would be researching the systems of control, which led to his to writing his book in Cybernetics. So, does information follow form, or does form follow information, or can it be? Is it both ways? I thought it was interesting when I was in Switzerland a couple of months ago. I happened to walk down one of the main streets of Zurich, Bahnhofstrasse, and I came across the entrance of this residential building. And as I kept walking down the street, I noticed that all the entrances would have this significant width where everybody would display, they kind of advertise their scientific expertise, because this is a street well known for bankers and doctors. So it was quite interesting to try and understand how, in this case, maybe information follows form. Within architecture, everybody knows the famous quote by Louis Sullivan, which was "Form ever follows function." Louis Sullivan was an architect who worked mainly during the late 19th century, and in his case, what he would consider the driving force behind a project would be the programmatic requirements of the building. In other words, form follows function would dictate that the aesthetics or external appearance of a building would somehow reflect the internal happenings, the internal layout of its spaces and its program. Another early proponent of not necessarily technological forces, but natural forces within a broader context was the Scottish zoologist Darcy Wentworth Thompson, who wrote a treatise in 1917 called On Growth and Form. So in this case, we're talking about technology as we're looking at natural ambient forces as the technology which are shaping the environment and shaping the way we look at things. And his project was the analysis of an organism development through a process which he called conformal mapping, which would take a Cartesian grid and try to deform different shapes to demonstrate how things may evolve from one stage to another. So there have been already, as we see, different notions, different ways that people have been thinking about what causes form to occur. This is a recent book by Georges Legendre, who is a professor at the AA in London. And this book is called Pasta by Design. So I thought it was interesting to show how all the different subfamilies of pasta are actually relying very heavily on some very explicit mathematical functions. So in this case, mathematical equations would be the driving technology, the project being the pasta itself. This is a project from, I think, a student in an Israeli university, design university, who used analysis software to actually map personal statistic data and embed it within everyday objects such as flatware. So you see a cup which was designed based on some particular statistics and a series of mugs which are showing some kind of evolutionary development from the smaller to the larger. So in these cases, I've tried to identify what kind of interface are we looking at. In this case, it will be a various series of softwares which is unknown. But I will try as we go on to try and see if we can identify some of these particular tools. Again, can form follow data. And by data, I would like to expand it to the notion of information in general. In this case, the technology being scientific instruments, various scientific instruments constructed during history. The first one being a device for plotting the integral of a graphically defined function that was designed by Bruno Bakanovic in around 1880 in Poland. The second one is a planimeter for measuring spherical curvature designed by Amsler in Schaffhausen, Switzerland, around 1889. And I think both show how an extreme degree of complexity in the appearance of an object may be the direct result of the information that it's meant to be communicating, but also the information of the knowledge which has been a result of. Moving on to graphics and statistical analysis, I thought these were quite interesting diagrams because, again, they, much like the flatware that we just saw a little earlier, but albeit in a slightly different way, they're demonstrating the expression of statistical data to create graphic diagrams. And in this case, technology being statistics, and the project is the actual visual representation of numerical data. The first is a poem which is arranged on a circular path using numerical values assigned to every letter of the alphabet. And the second is a three-dimensional representation of Earth based on a site-specific birth rate algorithm. Can form follow culture? Can culture act as a role of technology in this case within our argument? And I think it's interesting to see collective conscience as a technology in this case, whereby if we look at various African tribal scarifications, which are considered by the tribes as distinct marks of the passage from passage to adulthood. In this case, form following the cultural development and the historical development over time in various parts of the world. The interface being manual skills, obviously. So what would be some of the applications of technology within academia? I have tried to make a separation and unification of technology as software and technology as hardware, because this is something that everybody is familiar today. And I'm trying to make some relations, not necessarily within architectural domain, as I mentioned earlier. So this is a diagram of photochromatic analysis for a Gothic cathedral done around sometime around the 1970s. The software interface is unknown. We can see that it's somewhat primitive at the same time. It's very interesting that if we go just 30 years back, we already begin to see applications which are now ubiquitous. So in this case, the technology being the software and the project being structural understanding of particular edifices. Within my own teaching, I would like to just demonstrate a few examples of student work which have been looking at software and hardware as the driving force behind generating concepts, not necessarily in terms of their representation, but in terms of their generation. And here I would like to make a distinction between technology as the tools to represent and technology as a tool to generate, as a design morphogenetic force, if you wish. In this case, this is a project which was done by a student in a class which dealt with biomorphic influences on design processes, on design methodologies. And I'd like to mention that this course was supplemented by a lecture from an evolutionary biologist, and the project relies heavily on that information. The lecture was focusing on genetic tinkering, what he called genetic tinkering, which is essentially a series of means that, a series of factors which cause genes to change in amount, position, time, whatnot, to affect mutations within the human body. So the students were given a line and asked to actually generate a space based on some kind of evolution that this line could acquire through taking into account these particular genetic factors. So in this case, the technology is 3D modeling software, but the key being that it's being used within a particular conceptual framework, that framework in this case being evolution. And the mode is these conceptual parameters which are based on other disciplines, other than architecture in this case, and particularly genetics and biology. Another project which I'm currently working on is a pilot kind of study using a software which is, again, non-architectural, but can be, I think can be of great benefit for design-related courses, which is analysis software. I'm currently teaching a class called Bioprototypes, where we expand on the consideration of biological influences within design to exceed beyond that of biomorphic understanding and move on to kinetic devices. So I would like to briefly talk both about the content of the course, but also about the interface. This is some images from a recent webinar which we conducted in the classroom in order to teach especially software that deals with finite element analysis, which is essentially a tool to provide structural calculations that otherwise are not possible within any kind of conventional architectural or CAD tool set. So the interesting thing being that in this case we were able to remotely observe, both myself and the students, the tutorial, which lasted for about an hour, the instructor being in California, and so the conclusion being that I think webinar is not necessarily something new, but in this case, it provided a very handful platform for being able to communicate particular skills which are not necessarily available within our own campus. So the particular project in question dealt with the software called Scan and Solve, which essentially does structural analysis, as I mentioned. And so the technology is something which is derived from in the engineering domain and not necessarily from architectural design, other design-related fields. And the mode for the instruction was a plugin that comes in as a plugin for the existing software that we already possess. The project being the design for a column based on some kind of evolutionary process, similar to the linear morphogenesis that I just demonstrated a little while ago. But in this case, the form would be following not only concept, but also data. So this exercise unfolds in two parts, and it's kind of, I'm looking at it as a kind of experimental design exercise. The first part, during the first part, the students are asked to intuitively design a column based on what we perceive as elegance and beauty. The second part being designing that column based on feedback that they receive from the particular software in question. So in this case, they're using specialist data to inform their design decisions in a very conscious way. In the former case, they're using their intuition and their already acquired skills as designers in order to design what they think may be efficient. And ultimately, it may be very interesting to compare the results between the two different processes. Just to give you a brief idea about how the software works, you would import or model any kind of shape in 3D, then you would select the interface, which is just another pop-up window within the software, and you would have to choose a certain number of parameters before the analysis is executed. In this case, one of the basic parameters is obviously the force definition, so the amount and direction of the force. In this case, you can see you have a vertical force, which is applied to these particular points. This would be, and then you have to also select the restraint points, which means where is the object fixed, or is it freestanding. So in this case, we have restrained this column and beam to the side and at this point at the base. The second diagram actually shows the structural calculation with the various gradients of the colors ranging from the strongest being the blue to the weakest being the red. So it's clearly, as one would expect, the weakest point being where the beam becomes more slender just before it joins with the vertical shaft of the column. Now the interface goes a little further to actually allow for the selection of materials. So I'm not sure if anybody can read this, but there's an extensive list of materials from various types of aluminum, steel, concrete, and so on and so forth. And then you'd have the loads and restraints, and you have another set of factors such as gravity, which you may switch on and off, and then you would go to actually calculate the data. So in the case of this particular project, the students would design an iteration, then they would run it through the simulation within the plugin, and then they would revisit their design, and then so on and so forth. And so within a certain number of, finite number of steps, they would have a very informed understanding of whether the design is working or not. And this is something which is not available currently within any kind of architectural tool set. So it's very interesting that these tools have been available. Such specialist analysis software has been available and used in engineering for a very long amount of time. But I think there's a lot of potential for other professionals to tap into, such as architects or industrial designers, for example. So in this case, what we have concluded is that apart from using the particular technology within our own domain, it will be necessary to also physically collaborate and consult with experts who have been using such tools. In this case, we would be required to consult with a civil engineer. So currently, I'm trying to coordinate with one as the project proceeds. So what can we gain from that? I think there's a lot of potential to actually create new courses, elective courses, which are co-taught by faculty from various departments. In this case, we could begin to discuss the possibility of architecture and biology and engineering coming together, where a biologist could inform the evolutionary conceptual way of designing an artifact, the architect being the designer and the engineer being the consultant during this project. But also at a student level, I think these elective courses could or may not be offered jointly within different departments to promote student engagement among various disciplines. If we look at technology as hardware, which is something that we've always perceived as immutable and static in terms of our ability to interact with the software, with the hardware, meaning we always use computers for what they can do, but we are not designing computers themselves. In this case, the technology is a certain type of microcontroller, would be perhaps a better word, and which is called Arduino. This was from a recent workshop about a year ago where I had the chance to interact with this technology, and within a group of 3 people, the other 2 not being architects, but rather interaction designers, we were asked to design some kind of component using one of these controllers and a series of other elements which would kind of plug in to the main chip, that being the microcontroller, this being an accelerometer. Here we have a mini LCD display. So what we came up with within a few hours was the idea to create this mini bracelet that would depict a three-dimensional object on the screen. And as you would rotate your hand, due to the thanks to the accelerometer, that image would actually change. So you would perceive as if that object was morphing itself. This kind of technology, I think, unveils a lot of possibilities, and it's already used, to my understanding, within multimedia design and interaction design. But I think, what if we could, as architects, embrace it within some kind of more architectural design-related context? So within a simpler variation of the microprocessor, I was looking at Lego motors and how they can, because I was trying to understand what could be the simplest actuator that an architecture student could engage with in order to introduce them to this kind of interactivity within an elective course. So within one of my courses, I delivered this project, which was called the Trivial and Non-Trivial Machines. The trivial machine is a metaphor, is an understanding of how machines operate, which was done by the cybernetician Heinz Forster, where he actually describes trivial machines as synthetically determined, history-independent, and analytically determined and predictable. In other words, a trivial machine would be a machine which would give you the same output for every single input. A non-trivial machine would be a machine which is unpredictable, in other words, giving you various individual and different outputs for every single input. So the students were asked to design two types of machines, one being what we call the biological machine and the other one being a non-trivial machine, using a simple Lego motor as an actuator. These were four of the examples of the projects that they actually worked on. The first is the machines A and B are the biological machines, and machines C and D being the non-trivial machines. The first is a machine which kind of mimics the behavior of a Venus flytrap through this elaborate set of gears which were constructed out of laser cut cardboard. The second one being what we nicknamed the robo-jelly, trying to sort of mimic the movement of the locomotion of a jellyfish. And then the two non-trivial examples actually required designing an elastic belt which would move according to a certain mathematical equation. And example D, which is actually shown here, would be a moving assembly for a pattern that would be drawing based on randomness on a blank canvas, which is the project I would like to discuss a little bit in more detail. These are some images from the Robo-Jelly project, where you can see the Lego motor embedded within the acrylic components, which were all laser cut. So this was done within a digital fabrication elective within that kind of a context. And here we have a family of Robo-Jellies suspended from the ceiling of the Second Avenue Art Gallery during an exhibition which we had last year. So in this case, the technology being something very simple, as simple as the Lego motor, and the project being the Robo-Jelly installation. For those of you who are already getting bored, I have here something that you can begin to interact with, just in order to understand the simplicity, but also the simplicity of the machine, but also the complexity of the possibilities that can be introduced by this one additional parameter. So the project, the last project that the students negotiated was the non-trivial machine with the pattern drawing, and the understanding being that what they tried to do was essentially to map the movement of a known shape within canvas when that shape begins to collapse by introducing flexible joints along the way. So in this case, we have a square which, as the motor begins to introduce movement, begins to collapse in unknown patterns. And I think this is also demonstrates the designer's intentions towards the observer to create familiar associations within this system, and tracing this particular shape during the process of movement. In this case, what we were interested in was how does the observer perceive what's the experiential value of that particular construct as it is happening during time. Does it increase the ambiguity? Does it become more enigmatic? Or are they able to actually decipher what's going on? So here you see some of the schematics of that machine, where there is the Lego motor is transmitting the movement through a series of gears, which make this lever rotate around itself 360 degrees. Every time the lever rotates, it pulls a number of strings, which actually is helping to move this kind of assembly vertically. This kind of assembly is then dipped into this container with engine oil, and as it retracts back up, it draws on the blank canvas. So here you can see the machine in operation. It was very complex to actually create the painting, but we began to understand what the disadvantages or weaknesses of that particular design were in order to kind of optimize it and create a second iteration. In this case, you can see the movement always highlighted in bold of every one of these 4 steps. And in this diagram, I'm actually overlaying all the layers of movement, thereby connecting the points of the orbits of the moving points to create this kind of artwork, which relates directly to the process, which has created it. So, as a conclusion, I'd like to kind of clarify. This project was presented in a non-architectural conference, and I thought that was very interesting because the conference was focused on interaction design. The attendees were mostly computer scientists, interaction designers, multimedia designers, and artists. I was pretty much the only architect, so it was very exciting to receive feedback from a non-filtered audience, so to speak. And I think we have to understand how important it is that the feedback received can reach beyond our immediate expertise and can unveil opportunities that are otherwise not anticipated, thereby creating some kind of emergent effect. So in this case, just to recap, the technology has been microcontrollers, actuators, sensors of any type. And much like the software, the case with the structural analysis software, I believe that such technologies have the potential to encourage the creation of new courses, elective courses, which are co-taught. So in this case, the faculty could be from design-related fields as architecture and multimedia, but obviously that can expand to include many more disciplines. At the same time, since I'm always trying to balance the faculty and the student engagement, I think it would be a great opportunity to have students who have such expertise in actuators engage with architecture or design students to help enhance and optimize this kind of work. This is a project which was another collaborative project which we finished last year with the Department of Mechanical Engineering. The technology in this case is both software and hardware, but I think it transcends that to actually, so I'm trying to frame it within, or call it the cross-disciplinary expertise. And the project was the design and prototyping for a race car for SAE racing. Here you can see the finished race car, which is obviously constructed and designed and constructed by the mechanical engineers. What the architecture students contributed was the design and prototyping of the body shape. So we have here a couple of different versions of that were designed during the academic year, and physical prototypes were then created, and simulations were executed within the wind tunnel. And all of these facilities are based within the mechanical engineering department, not the architecture department. But we thought, and I've tried to include this image here, which shows actually the name of the School of Architecture on the car, because it relates to the, I think it clearly demonstrates the importance of having such research endeavors which transcend the immediacy of our own scope of focus. This proved also to be a great experience for the students. So this is a project that has been ongoing this year as well, and we are looking for people who are interested in engaging with us, which are not necessarily from the mechanical engineering or architecture departments. So In this case, technology for the race car project has been the various CNC manufacturing techniques, the computer numerically controlled manufacturing techniques, but also other manufacturing techniques which have existed in engineering, more conventional prototyping and so on. And for us, it's interesting to acknowledge that architecture has been using these kind of technologies within the last 10 years, but they also have existed, much like the structural software that I mentioned earlier, within engineering domain for more than 30 or 40 or 50 years, but within an industrial scale. And now everything is coming to us from that kind of background, and as architects, we're beginning to look at it from another perspective and at a different scale, and considering different tolerances. So I think there is a huge potential here to initiate various set of research projects which are jointly supervised by faculty from more than one departments. Again, the ones that come to mind first would be engineering, multimedia design, biology, but computer science also, and obviously I think business would always be handful during the design and management of such a project. So, and again, the students from more than one department would be would have the possibility to benefit from such a collaboration, as have the students who have worked in this project done so far. So I'd like to finalize by showing a project from a researcher at the MIT's Media Lab. And the Media Lab has been, as some of you may know, one of the first proponents of collaborative schemata within research. It was initiated during the 1980s, and they're currently offering a degree in what they called media arts and sciences, which essentially incorporates architecture, engineering, design, computation, biology, anything you can pretty much imagine. And as a matter of fact, there was a course at some point offered within the Media Lab which was called How to Design Actually Anything, which I found somewhat amusing. This is a project by Neri Oxman, and it's a project for a lounge, for a chaise lounge, which I will read the description from the actual book. It says that chaise incorporates structural, environmental, and corporeal performance by adapting its thickness, pattern, density, stiffness, flexibility, and translucency to load, curvature, and skin pressured areas respectively. It is textured with 5 different materials of various elastic moduli. Stiffer materials are dark colored, while softer materials are light colored. So in this case, Neri collaborated with medical experts and computational experts and computer scientists to create an algorithm that would map the materials on that particular surface based on the pressure points and the pressures that the skin actually needs to, that the body needs to adapt to. So you can see there that this is important both in terms of the actual technology that is implemented, which includes various materials, 3D printing using various materials, which is a very innovative technology. It didn't exist a couple of years ago. And also, it's a project which includes the expertise and consultation from various scientists. It's now displayed at the Boston Museum of Science, and I thought that the title of the project was quite interesting, which is called Beast. So again, this has been another project which demonstrates the strengths of a synthetic kind of way to look at the way we design, the way we do things. So in this case, we have seen form follows material properties, and that has begun to demonstrate the rise of this kind of synthetic working paradigm among various experts. I think the quote by Richard Buckminster Fuller, who was an architect, but much more than that. He was a mathematician, he was a scientist, he was a designer and engineer. He tried to define what architecture is. So what he said is, a designer is an emerging synthesis of artist, inventor, mechanic, objective economist, and evolutionary strategist. So we are trying, or may have unconsciously or subconsciously tried to address all these various areas within our distinct trajectories of work. However, it becomes clear today that we also need to actually physically interact with all these people, the artist, the inventor, the mechanic, the economist, to actually receive that passive consultation and optimize our own projects. So to recap, we began from what I would like to call the pre-digital culture, form follows function, to a post-digital culture where form can follow expertise and promote integration. So what I'd like to iterate is that the use of technology can be just as beneficial for students and faculty alike, depending on the way that we design the teaching frameworks within which we operate. And there may be various analogies that can be made to include several academic departments. I've tried to mention some of them here: architecture, engineering, multimedia design, architecture, biology, computer science, medicine, engineering, computer science, mathematics, design, industrial design, and material science, whatnot. So where does this end? I think all these various innovative ways of looking at working among different experts could promote an emergent research trajectory in addition to one's typical area of study. And by emergent, I think it's the value of an emergent context lies in the unknown aspect, in its unknown proportion. It's something that we have not yet come to understand. It's something that may create solutions to problems that we are not even asking the question to. So I think this can be encouraged by both active and passive consulting, which also may translate into filtered versus unfiltered research venues, conferences, etc. So I encourage you all to go and attend an architecture conference, and I myself am trying to shift from directly architecturally related venues to more broad ranging frameworks of discussion. So I'd like to remind you all that it's important to collaborate, but it's also important to collaborate efficiently. So we are supposed to look for expertise, but what is the appropriate expertise? What does it require? I think we need careful filtering and selection of collaborators. I'd like to refer everybody to Nicolas Negroponte. There's a typo there, I'm sorry, it's called Nicolas Negroponte, who was the founder of the Media Lab at MIT, and his book of Being Digital. So I would like to end my presentation, if you don't mind, by reading a very short paragraph from his book, Being Digital, where he tries to explain the importance of filtering information and the importance of acquiring the right type of data in order to make any kind of decision. So this is from a chapter which is called Digital Butlers. In December 1980, Jerome Weisner and I were the overnight and dinner guests of Nobutaka Shikanai at his lovely country house in the Hakone region of Japan, not far from Mount Fuji. We were so convinced that Mr. Shikanai's newspaper and TV media empire would benefit from being part of the inception of the Media Lab that Mr. Shikanai would be willing to help pay for building it. We further believed that Mr. Shikanai's personal interest in contemporary art would play right into our dream of blending technology with expression, of combining the invention with the creative use of new media. Before dinner, we walked around Mr. Shikanai's famous outdoor art collection, which during the daytime doubles as the Hakone Open Air Museum. At dinner with Mr. and Mrs. Shikanai, we were joined by Mr. Shikanai's private male secretary, who quite significantly spoke perfect English, as the Shikanais spoke none at all. The conversation was started by Weisner, who expressed great interest in the work by Alexander Calder, and told about both MIT's and his own personal experience with that great artist. The secretary listened to the story and then translated it from beginning to end, with Mr. Shikanai listening attentively. At the end, Mr. Shikanai reflected, paused, and then looked up at us and emitted a shogun sighs. Oh. The male secretary then translated, Mr. Shikanai says that he too is very impressed with the work of Calder, and Mr. Shikanai's most recent acquisitions were under the circumstances of, wait a minute, where did that all come from? This continued for most of the meal. Weisner would say something, it would be translated in full, and the reply would be more or less an "oh," which was then translated into a lengthy explanation. I said to myself that night, if I really want to build a personal computer, it has to be as good as Mr. Shikanai's secretary. It has to be able to expand and contract signals as a function of knowing me and my environment so intimately that I literally can be redundant on most occasions. The best metaphor I can conceive of for a human-computer interface is that of a well-trained English butler. The agent answers the phone, recognizes the callers, disturbs you when appropriate, and may even tell a white lie on your behalf. The same agent is well trained in timing, versed in finding the opportune moments, and respectful of idiosyncrasies. People who know the butler enjoy considerable advantage over a total stranger. That is just fine. Such human agents are available to very few people. A more widely played role of similar sorts is that of an office secretary. If you have somebody who knows you well and shares much of your information, that person can act on your behalf very effectively. If your secretary falls ill, it would make no difference if the temporary agency could send you Albert Einstein. This issue is not about IQ. It is shared knowledge and the practice of using it in your best interests. Thank you. Any questions?
So what's the student engagement been like? I imagine they get pretty excited.
They're very enthusiastic. At first, when they see the complexity of the projects, there is a sort of step back at in the end. I think so far all the results have been quite astonishing for myself. So it's clear that we would like help from other consultants, either having a person from another department come and teach some aspect of the course, or have them give a guest lecture, or I think it would be interesting for us to do the same thing, whenever that may be possible.
And the access to the technology and the processes, like I know you guys have the laser cutter and the router, and now you have a 3D printer. Like, is there equipment that you would push for, or has that really helped to inspire some of these projects?
I think because, as I said, we've moved to this kind of what we call now, we like to call it post-digital culture. Things have shifted so fast that even now the laser cutter and the 3D printer are nothing special. So the current paradigm of within architecture, at least, as far as I know, is that of integration. And we're trying to invent new technologies or new methodologies that would help implement the technologies that we already invented. So the laser cutter and the 3D printer have been in use within design for the last maybe 5 to 10 years. So now we're trying to really expand a little bit on that. And that can happen through by changing our conceptual framework. And that would need to bring in something from outside the boundary of architecture, in which case either that being the simulation software or the kinetic hardware or any sort of other devices which may enhance and augment the possibility for architectural design. Okay, thank you.